Welcome everyone to the OWASP Los Angeles, November 25th, Thanksgiving meetup. And we are very pleased to have a great speaker today. But first of all, I would like to remind everyone that we're having a joint meetup coming up on December 30th between ISSA and OWASP. And we have a great topic, which is Good Riddance 2020. It's been a tough year for a lot of people for a lot of different reasons, but we're going to drink 2020 goodbye. We encourage folks to watch out for our meetup notifications about this event. Basically, we'll be using Discourse as the back end, and we'll have several rooms where you can decide to join us. We'll have different topics such as music, a few other things. This will be just a purely social engagement for all of you to enjoy yourselves with. I think we'll all be looking forward to this. It'll be at 5 o'clock Pacific time. So again, stay abreast of your notifications. And so with that, I would like to then turn over the meeting to Daniel Lehmann, who's going to talk about binary security. We're very pleased to have Daniel joining us today from Germany, where he's enjoying life in COVID. We're really pleased to have you. It's one of the advantages that COVID does bring to all of us, which is the ability to have people from around the world to speak to us and share their experiences and their ideas. And so, Daniel, welcome. OWASP LA is privileged to have you join us.
All right, thanks so much for the introduction, and thanks a lot for having me. That's really great. So as Rich mentioned, I'm going to talk about binary security of WebAssembly. I'm a PhD student at University of Stuttgart in Germany, and I'm really happy that I can bring some of the kind of academic research away from its ivory tower more into kind of the hands of practitioners, and I'm really glad to be here. So of course, this is not just work done by me, but also done by collaborators and my advisors. So we were collaborating with Johannes Kinder from Bundeswehr University in Munich, also in Germany. And my advisor is Michael Prapel from University of Stuttgart. And this whole work, this is titled Everything Old is New Again, Binary Security of WebAssembly. And that's a paper that we recently published at Usenik Security, an academic security conference. So before I go kind of into the technical depths and bits of our paper, I want to make use of the a bit more time that I have here in this setting, which is really great. And that is why I split this talk into 3 parts. And the first one is going to be about WebAssembly in general, because I assume maybe not everybody has heard of it, or if everybody has heard of the term, then possibly not everybody has fiddled with it in depth and maybe compiled some programs to it. And so I want to cover a bit of background on WebAssembly in general. Then in the second part, I want to talk about WebAssembly and security, because I think there's quite some misconceptions or misunderstandings in the past, because WebAssembly has been advertised as secure, and I want to kind of discern a bit more what it is secure against. And there's 2 kinds of security for WebAssembly. One is called host security, and as the title of the talk tells you, we are more concerned with binary security. And that's what I want to cover in the second part. And then the third part is going to be about our paper and our research in depth. And that is what findings do we have. And I also want to give you a little demo to show you that it's not only theoretical, but it can be actually exploited in practice. All right, so with that out of the way, let me get started with the general background on WebAssembly. So I guess, especially as security practitioners, whenever we hear of a new feature in a web setting, especially, we should always ask, oh, adding more features that increases our attack surfaces. Why is it even necessary? So why do we need WebAssembly? And I think there's a couple of good reasons why we want to introduce a new language in the browser. And that's what it is. And the reason are threefold. And they're all tied to the only option that you had until now for executing programs in the browser, and that was JavaScript. So JavaScript has a couple of shortcomings. Some of them have been very well presented in this blog post by Lynn Clark. And some of them are tied into performance first and foremost. So as we know, JavaScript is a source code format. You can read it as a human, but unfortunately, that means that parsing it and compiling and optimizing it is quite slow. And WebAssembly is aimed to reduce this parsing time, for example, and also it doesn't rely on just-in-time compilation, garbage collection, and so that means that WebAssembly execution is much more reliable in terms of performance. You will always have a reliable, relatively close to native execution performance, and that's great. And then the third reason why you might not be so happy with JavaScript is that it was your only option until now, and often it was a bit abused as a compilation target. It was never really meant to be the only language, and so people maybe want a language with more features, or they want to program in a different language because that's what they are used to from their backend programming. And then you can compile to JavaScript, but it was never really meant to be a compilation target. And that had a couple of downsides, and WebAssembly tries to remedy that. Now, there have been other technologies in the past that try to complement JavaScript, and one branch has been famously a security nightmare. So that has been ActiveX plugins, Java applets, Flash, and so on. And those have always been very problematic because they could, if you didn't update your plugins in your browser, it could lead to remote code execution and so on. And so those have been disabled by now, and basically none of those are in use anymore. Another branch was native client and portable native client, but those have only been used in Chrome and never been available for Firefox or Edge or IE. So in a sense, those have never really been adopted in the web in broad terms. And then a similar fate has been by Asm.js, which again was another language that was meant to be fast to execute and compact and so on. But that was not really supported by any browser besides Firefox. So all of those technologies have not really caught up, and WebAssembly is finally here to save us. And that has been going on. WebAssembly has been going on for quite some years now. So it has been originally announced in 2015, and all the major browsers support it now since 2017, which is since quite some time. There has been an academic publication, which is really great to read up on its type system and the general design behind the language. That's also from 2017, and it has been officially standardized by the W3C in 2019. So I think it's safe to say that it's really an established standard by now. And we can also see that on two small data points that I bring here. One is that what we did was we looked at the top 1 million websites and looked at how many of those use WebAssembly binaries, and we find 50,000 usages. So certainly it is used in practice by large websites. And similarly, if you look into the client-side support, you can, for example, go to Can I Use and check how many browsers do support WebAssembly. And we see that I think this was in October when I checked, 93% of all global browser installations supported natively and can execute WebAssembly programs in your browser. And that's certainly a large share, and that even holds for mobile browsers like Chrome, for example, on Android. So that's kind of all the motivation. Why do we need WebAssembly? Now, what is it actually? And for that, I just want to give you a very kind of brief 1-minute introduction. So what you can see here is a very simple program, a function in WebAssembly that takes an argument and adds just one to the argument. And the first thing that becomes apparent is that this is a very low-level language. You have to manually load arguments. You have to manually push constants on a stack, and then you have to manually perform an addition operation. So it's certainly much more low-level than JavaScript. So that means you wouldn't want to write this program by hand, but rather you compile to WebAssembly. And typically you can compile from, say, C and C++ code, like this example program on the left. And then I also mentioned that WebAssembly programs are delivered as bytecode to save the browser from having to parse this source code format. So in fact, this is not in the middle. This is not what is being delivered to the browser, but instead it's this binary format on the right. But there's a one-to-one mapping between the two. So this textual representation is called the WAT format, and the binary format is the actual WASM binaries. A couple of other language features that WebAssembly has, just in case we are not aware of them. So one thing that we see is that operations in WebAssembly are performed on a stack machine. So for example, here you see that the first instruction is pushing some value on a stack, and then there's another value pushed on the stack, and then finally this instruction, this add instruction, removes the two arguments and adds them together and pushes them again on the stack, the result. And this is, of course, much more low level than, for example, in JavaScript, where you can build up complicated expressions. What we can also see from the example on the right is that WebAssembly programs are statically typed. So, for example, this function parameter or the function result, we see those are 32-bit integers, whereas in JavaScript, we have dynamic types, and those can change at runtime. And the good thing about static typing is, for example, that WebAssembly programs can be ahead of time compiled by your browser to very efficient machine code. And that makes why WebAssembly programs are typically much quicker to execute than JavaScript. Another reason why WebAssembly is quicker to execute is that it doesn't rely on garbage collection. Instead, it just has one flat linear memory, one array of bytes, essentially. And the WebAssembly program has to manually work with this array of bytes and manually allocate objects in this flat memory. And we'll see later how that affects security of WebAssembly binaries. Okay, and the final thing about the language is that it is very restricted, and deliberately so. So a WebAssembly program by itself is pure computation. There's no standard library or no fetch API that you can call, or no browser API by default. But if you want to do anything with the underlying system from a WebAssembly program, you have to import some functions from what we call the host environment. So say you are executing WebAssembly in the browser, and you want to perform network I/O, then you need to import this fetch function from the browser, from the surrounding host environment. And without that, WebAssembly is just computation. There's no standard library. So that was kind of about the language itself. Now a bit more about the ecosystem around it. And one thing to look at is which languages are targeting WebAssembly, can be compiled to WebAssembly. So which languages can I write and then compile to WebAssembly? And what we have done, this is actually another work in progress that I'm doing research on. We have looked into the top binaries that we collected on the web, as I showed you earlier. And we've looked into which languages were used to compile them, or where they compiled from. And you can see that a large fraction of binaries are compiled from C and C++ programs, but there's also other languages like Rust, or even Go and AssemblyScript, and even some more obscure languages like Kotlin or COBOL even. So what I want to take you away from this is that WebAssembly is really a great compilation target and can be targeted by many different languages. And then the second aspect is not only who can produce WebAssembly, but also who can consume WebAssembly, who can execute it. And as I said earlier, WebAssembly is originally designed to be executed in browsers on the client side. But recently, it has also been picked up on different host environments. And one is, for example, Node.js. So you can execute, say, some cryptographic algorithm or some computation-intensive part of your application in a WebAssembly program inside your Node.js package. Or Cloudflare has an offering, I think, for their function as a service offering, where you can ship WebAssembly binaries and they execute it in their data centers. And I think the same goes for Fastly. So there's quite some interest in using WebAssembly on the server side, not just on the client side. And the third big group of host environments are standalone VMs, so not tied to the web setting at all, just kind of like a regular VM language like Java, for example. And there's even a bytecode alliance, which is, I think, founded by Fastly and Intel and Red Hat and Mozilla and so on. And they have published a couple of standalone VMs like Wasmtime and Lucid. And with those, you can execute WebAssembly binaries just as if they were regular native programs. And one particular use case of those standalone VMs or out of web settings are smart contracts or cryptocurrency systems. So if you look at the top 13 cryptocurrencies, you see that 2 of those currently use WebAssembly EOS.IO or plan to use WebAssembly as a bytecode Ethereum. So I think that goes to show that WebAssembly is tremendously important already now on the client side, but also expanding to different settings. So I just see a question in the chat. So if anybody wants to have a question, just write them down, or you can go ahead and ask them. I'm really happy to take them also during the talk. So in case anybody wants to ask a question, go ahead.
Oh, if you want to ask a question, just unmute yourself. Yeah,
Sure.
Daniel, it's fine with questions in the middle of presentation.
Yeah, hey Daniel, it's Paul. So just a quick question. You mentioned about C, C++ being a big part of compiling and deploying it. I'm just curious, would some of the security issues that are typically innate with C, C++, like buffer overflows, would that also be security issues related to WebAssembly? You may touch upon that later, but just curious.
That's a wonderful question. That's exactly kind of the core technical part that I come to in the last kind of half, I would say. So yes, absolutely, yes. And we'll
okay, thanks.
All right, so what is WebAssembly being used for now? You can play 3D games in your browser. You don't have to install anything, and those are powered by WebAssembly, like famous game engines, even like Unreal Engine or Unity. Google Earth uses WebAssembly. Hangouts, Keep, all Google applications, all those Google applications use WebAssembly as well. You can even compile codecs to WebAssembly. So say you are a video portal and you want to send a very highly compressed video stream to your client, but the client doesn't support this video format, then you can deliver a codec as well as a WebAssembly binary, and he or she can use that to decode the video. And you can even run programming language implementations and compile them to WebAssembly. So there's a Python implementation that's being compiled to WebAssembly, and then you can run Python programs on the client side in your browser. And finally, you might use WebAssembly already now without you knowing, because some JavaScript libraries are using WebAssembly parts for the computation-intensive parts of their library. So Hyphenopoly is a hyphenation tool, so it automatically breaks and splits words, and it uses WebAssembly to do that efficiently, even though it appears to be a JavaScript library. All right, so that's kind of WebAssembly in general, and kind of the takeaway message from my side is that I believe it's a very cool technology, and I believe it's going to be hugely important in the future, and it already is quite important and quite well used right now. So given kind of the host of this meeting, certainly we should wonder about what implications does this have for security, and that's kind of the second part. And Paul, in his question, he already touched upon one aspect of security. And I think it becomes pretty clear when we look in the application domains of WebAssembly that security is super important. So on the client side, you're always executing untrusted code. So if you are executing some arbitrary WebAssembly program, you really want to make sure that it doesn't mess with your system, right? And the browser is installed on basically every device on the planet. So certainly we need to think about security there. On the server side, the same thing goes. If your server handles kind of untrusted input from requests and hands that over to a WebAssembly part of the service, you want to make sure this can't mess with the rest of the system. And finally, in smart contract systems, well, you're handling large sums of money, so certainly you should care about security as well. And what I want to say right from the start is that security has been a concern in the design of WebAssembly as the language. And you can see that in the academic publication on the left, and you can also see it prominently featured on the official website of WebAssembly, that they all mentioned safety and security right from the start. And so it is true that people have put thought into it, and they have learned from past problems. So for example, WebAssembly is not a third-party plugin in your browser, but it's basically a new front end for the JavaScript engine that is already in there and that has been tried and tested, and that's been regularly updated together with your other browser components. So that's very good. As I said earlier, WebAssembly programs are type checked before they can be executed. And that also goes and removes some potential exploitation capabilities. The WebAssembly language also doesn't make it possible to mix code and data. So at runtime, you can never inject additional WebAssembly code into a binary. The code is fixed from the moment you load the WebAssembly program, and you cannot add data, code later. And finally, as I said earlier, WebAssembly is pure computation. So whenever you want to do some I/O or some other modification of the surrounding system state, you need to do so by importing host APIs. And then in the browser, those host APIs are just the regular JavaScript browser APIs. So if a WebAssembly program wants to do a network request, it needs to import the fetch JavaScript function. And this function is just under the same security model as all JavaScript code is. So WebAssembly programs, as long as the implementation is correct and so on and so forth. WebAssembly programs can do only as much as arbitrary JavaScript code can, which is all good. And all of these security features are great, but they all work under the assumption that WebAssembly is malicious, that I need to defend myself or I need to defend the host against malicious WebAssembly binaries. And another instance of this attacker model of malicious WebAssembly is cryptojacking. So in the last year or last 2 years, some websites have used WebAssembly to mine cryptocurrency in the background in your browser window while you are visiting a regular website. And you maybe only realize that because your fan is spinning up, or you're suddenly wondering why your computer is so slow. And certainly that's unwanted. And that's another instance of a malicious WebAssembly program. And there has been a whole line of work of detecting and defending against this kind of exploitative behavior. But again, this is only malicious WebAssembly. And what I really want to drive home with this slide is that this is only one side of the security coin. So a lot of work has been worrying about the security of the host and about malicious WebAssembly. But what much less has been put under scrutiny or has been analyzed is the security of WebAssembly programs themselves. So as Paul already mentioned, what happens if you compile a C and C++ program to WebAssembly? Is it still secure, whatever that means, right? And that's exactly kind of the core part of our research. And that's what I want to go into in the technical part of my talk. Any question that you might have until now? All right. So with that, let me come kind of to the core technical parts of our research project and our paper. So as I said, most WebAssembly is compiled from C and C++, and those are famously memory unsafe languages. And for example, and then we execute this WebAssembly binary, for example, on the client side or on the server side or in standalone VMs. And now our question is, especially if you look at this program here on the left, what happens if this source program has a vulnerability? So what we see here, for example, is we have a function. We assume it takes some user supplied input, this source string, and then it copies this into a fixed size buffer on the stack. And that's kind of a textbook buffer overflow. I'm sure this is in the OWASP top 10 even. And so certainly a lot of programs have suffered from it if it's even in one of those top lists, right? And what happens now if you compile this source program to a WebAssembly binary? And then later, an attacker supplies malicious inputs to the WebAssembly binary. And so what we see here is that this attacker model or this scenario is different from host security, because here the WebAssembly binary is not malicious, it's vulnerable. And the malicious thing is the input that's being supplied to this binary. Now, if we look at the C and C++ program, we know, of course, that when you compile this to native code, we've had a whole decade of cat and mouse game between attackers and defenses. And there's a lot of very good mitigations or hardening techniques that try to make sure that those bugs, those vulnerabilities are not exploitable if you compile the C program to native code. And there's a couple of defenses. There's virtual memory since the 80s. There's stack canaries since the 90s. And more recently, there's been much more elaborate defenses like ASLR and control flow integrity and so on. And the question is, are those mitigations also present when you compile the same vulnerable source program to WebAssembly? And some people might think, just because of the claims that WebAssembly is secure, that it is better than native binaries. But actually what we will find is that in some cases, it is not as secure as native binaries, because the native binaries profit from all these mitigations, whereas WebAssembly sometimes lacks them. And one kind of, or two data points for where people are overclaiming on WebAssembly security is here, for example, an official design document where we quote, a data execution prevention and stack smashing protection, so that's canaries, are not needed by WebAssembly programs. And we'll see later in the talk that this is not true. And a second quote where the PLDI paper says, at worst, a buggy or exploited WebAssembly program can make a mess of its own data. And we think that's actually quite bad. And it doesn't sound as innocuous as it sounds here. Or it isn't as innocuous as it sounds here. Okay, so what I want to show you from our research work is a couple of contributions. So one thing that we did is a security analysis of the language, and in particular, one feature of the language called linear memory. Then we provide you with a library of attack primitives, and you can combine those attack primitives, and then you can build exploits from those primitives. And what I also give in the paper, what we also give in the paper is 3 exploits on 3 different platforms, so that you can see that WebAssembly binaries are not just vulnerable in the browser, but also if you execute them on Node.js or potentially in standalone VMs. And I will even show you one exploit if we have the time as a live demo in a bit. And finally, we also did in the paper some measurements on real-world binaries. So all of this previous stuff is mostly analysis and arguments and understanding kind of the problems. And in the last bit, we also want to kind of quantify how high is this risk in practice. But the thing is, just because of time reasons, I don't want to go into all those 4 points in detail. So if you want to do that, of course, please always ask questions if you want to. Or alternatively, you can go ahead and have a look at our paper where we cover, of course, all of those 4 points. So in this talk, I will go a bit into the security analysis of WebAssembly as we go, kind of guided by examples. Then I will show you a couple of the attack primitives that we have. I won't have time to go into each and every attack primitive, but we'll cover kind of some of the most important ones. And as I said earlier, I want to give you an exploit demo, a live demo on one particular platform, namely in the browser, because I think that's maybe what is most important right now. Okay, so if you want to exploit a WebAssembly binary, we say you have to perform a couple of attack steps. And the first step that we always take in our attack framework against a vulnerable WebAssembly application is obtaining a write primitive. And one example primitive that I also want to show you and explain a little bit is a buffer overflow, just as Paul mentioned, on what we call the unmanaged stack. And I will go ahead and explain what that unmanaged stack is and how it can be exploited. And then the second step that we always take in our attack frameworks is overwriting some sensitive data. So having the write primitive is one thing, but the question is then, what do you overwrite with it? And what we do in this example exploit that I explained to you in a bit is overwriting heap data. And this is already curious or interesting because we use a buffer overflow on the stack to overwrite some data on the heap. And we'll see why that is even possible, because that is not possible for native programs, but it is possible in WebAssembly binaries. And finally, the third step in our attack framework is performing the actual malicious action. And in our example, this will be cross-site scripting in the browser, so abusing some imported JavaScript function. So say your WebAssembly binary is importing document write, and regularly it shouldn't perform a malicious action, but you as an attacker can maybe influence the string that is being written to into the DOM, and that gives you cross-site scripting capabilities. And of course, we all know that that's a huge attack vector and very dangerous. And I think it's even featured in the OWASP top 10 again. All right, so yeah, and one thing that I almost forgot is that typically between the first and the second step, there's a couple of mitigations, and those are present in native binaries, and we'll see in a bit whether or not they are present in WebAssembly. Any kind of question on the attack outline on those steps? Okay. So with that, let's focus on this first part, and that's how can we exploit the unmanaged stack. And in order to go into the exploit, I first need to explain what is the unmanaged stack in the first place. And for that, I want to explain the difference between managed and unmanaged data in WebAssembly binaries. So WebAssembly is a bytecode. It's an interpreted language or on a virtual machine. And some of the data of your program is managed by that virtual machine. And that can be, for example, scalar variables. So this defines a local variable of integer, 32-bit integer type. And this local variable can only be written by special get local and set local or set local, t local instructions and only read by get local instructions. And the actual place where the value of that local is stored, that is not accessible to the WebAssembly program. That's managed by the VM. So in a sense, this data is safe from being overwritten by a memory vulnerability. And similarly, some control flow data, so for example, return addresses, when you call a function and then you later return to the call site, this address is also managed by the VM. And that is really good because it means that it can't be overwritten by an attacker. However, what we also find is that a lot of data, actually most of the data, is not in those managed places, but it's rather in the linear memory of the WebAssembly program. And that is accessible to all memory operations of the program. And consequently, if you have a memory vulnerability, all this data can be modified. And so some examples of data that ends up in linear memory, all heap allocations, of course, then all data that is not scalar. So these locals, they can only have integer type or float type, but there's no complex data types in WebAssembly. So whenever you have an array, or if you have a struct or anything that requires more than integer type, then you cannot put it in a local, and then consequently it needs to be put into memory. And then it can be overwritten. This also goes for any data of which an address is ever taken. So if you ever have something, even if it's a primitive integer and you want to take a pointer to that value, well, a local or a managed value by the VM doesn't have a pointer, it doesn't have an address, so you cannot take a pointer to that value. So for example, if you have a function, even if it takes an integer by pointer, then it means this integer parameter cannot be put into locals, but it is put on the memory. And finally, this is even true for global data. So say you have a string literal in your program, hello world or whatever, then even this string literal cannot be put in some safe region, but it is just put in linear memory and accessible to all memory write instructions. And this is, of course, potentially dangerous. Now, one particular part of linear memory is set aside for the stack. And this is basically just analogous to the native stack. If you have regular native programs executing, whenever you enter a function, you allocate some space on this stack. And in WebAssembly, there's just the same stack as well. And it is in memory. And this stack is used, for example, for complex data structures and for any data of which an address is ever taken. And what we also find in our quantitative evaluation is that around about a third of all functions make use of this unmanaged stack. So it's by no means seldom that data lands in this unmanaged memory. Okay, so now with kind of this background out of the way, I want to give you an example how an exploit against a native program would work, and then how it doesn't work and how it translates to WebAssembly. So we come back to this C and C++ application that has a textbook buffer overflow. And if you compile that to native code, then you will have a stack, as I said earlier, in native memory. And for example, one part of the stack will be a stack frame, and this will contain local variables like this buff variable, which is 8 bytes large. And then an attacker can supply some data that is too large to fit into this buffer, and then it will overflow this buffer and overwrite data that is upwards of the buffer. Now in native execution, thankfully, we have a mitigation called stack canaries. And what this does is basically the compiler inserts into your machine code. It inserts special code that checks when you exit the function that the stack contains a particular random value. And if this random value is no longer present, or if it was overwritten by other data, then the program itself will detect this and basically abort execution. And this is good because it means that an overflow is stopped right at this canary. And then any data that lies beyond the canary, for example, return addresses, are safe from exploitation in native programs. And that's a good thing. Now, in WebAssembly, we also have a stack, as I said earlier. And this also contains local data like this buffer. And what I also mentioned to you earlier is that there is some managed data that is accounted for by the VM, and that cannot be overwritten by an attacker. And that is good because, for example, return addresses are part of this managed data. But the problem is that the unmanaged stack in WebAssembly also doesn't have stack canaries. So just to compare those two sides again, in native execution, we do have data in the regular memory, and in theory, it's susceptible to being overwritten, but we have a defense called stack canaries. In WebAssembly, some data is managed by the VM, which is good, but unfortunately, WebAssembly compilers do not emit this canary defense, and that means that an overflow can just proceed to overwrite data up the unmanaged stack. And this is even worse than in native execution because it can not only overwrite data in my own stack frame, but it can even overwrite data in the caller of a vulnerable function. So here in this example, we have a caller function. This calls the vulnerable function, and now the actual vulnerability is in the vulnerable function, but an attacker can overwrite even data up in the call stack. And that's much worse than in native execution, which is surprising if you think that WebAssembly is a secure language. Any question on that buffer overflow example?
I got a question, Daniel. So one of the old-time exploits that used to work was, okay, there's a canary, but if you keep overriding the memory, you're going to get to the exception handler. And
right.
So is this still present?
So WebAssembly right now doesn't allow you to, or you can compile C++ applications with this exception handling to WebAssembly. But I think it will just abort upon an exception. So there's technically no exception handling supported by mscripten, the main C++ to WebAssembly compiler in use today. So just because WebAssembly doesn't support exception handling, it also means this vulnerability goes away. But the question is what happens as soon as they support exceptions. So yeah, I don't know what the status on that feature is, but I think it's important to look at, for example, those analogies of old exploits that we've seen in native programs. Are they still applicable to WebAssembly? So I hope that answers your question.
Yes, thank you.
Sure. All right, so that's kind of the first part of the attack. Was we can see now that we can overwrite data on the stack given a stack-based buffer overflow, and stack canaries do not prevent us from doing so simply because they are not present in WebAssembly. Now, the second part of our exploit was overwriting some data with that stack-based buffer overflow. And what we targeted is heap data. And that's very surprising. And the reason is that in native programs, between the stack and the heap region, you typically have guard pages or unmapped pages. And as soon as a linear overflow would write into one of those addresses, your program basically crashes and stack faults, and then you cannot exploit that, right? But in WebAssembly, we have what is called a linear memory. And I want to give you a bit of background on that to understand why this is not how it works in WebAssembly. So in WebAssembly, all memory is a single contiguous 32-bit address space. And there's no, and all the unmanaged data that I explained to you earlier is in this address space. So for example, the unmanaged stack that I said earlier, and the heap, of course, and then also statically allocated data like string literals, for example. And the thing is that because this is a linear memory, every pointer between 0 and the maximum size of that memory, of the currently allocated linear memory, is valid. There simply is no way in terms of the language specification to mark regions of memory as unavailable or not mapped or anything like that. So whenever you have a pointer that is between 0 and max mem, you can write and read to that pointer. And this in particular means that there is no guard page between the stack and the heap. And if you have a linear stack-based buffer overflow, it means if you just keep on overwriting long enough, eventually you can even overwrite data in the heap. So this is what I said. There's no unmet pages between those regions. And now the final thing is that not only can you not mark some regions of memory as inaccessible, but everything always in that memory is always writable. There is no non-writable memory region in WebAssembly. And that is true even for supposedly constant values that are statically allocated at program startup. So when, say, your C program has a string literal, and that's going to be placed in the static portion of linear memory, then the WebAssembly language allows to override this portion of memory. There's nothing stopping you from there, and there simply is no way to specify a region of memory to be not writable. And finally, what we also see from linear memory is that there is no address space layout randomization as there is for Windows and Linux executables. And memory allocation is always fully deterministic. So if you know the program and if you know the compiler, you know exactly how large the static region is, where it starts and ends, and the same for the stack and the same for the heap. And I think even if you wanted to add ASLR to the WebAssembly linear memory, the problem is that WebAssembly has only 32-bit address space, and that typically doesn't give you enough entropy to actually effectively randomize the locations of those regions of memory. So this is also not present in WebAssembly memory. All right, and that's the reason why you can override from the stack onto the heap. And with that, I want to turn onto the third part of our exploit, of this example exploit, and that's actually performing the malicious action. And for that, I want to, before I show you the demo, I want to show you a simplified view of the code and what's happening at runtime. So what you see on the left side is an example web application. And you can write that in C++ and then compile it to WebAssembly. And in this example, let's assume you have some HTML string that contains an image tag. And then you take from the input, from the user as input an image, for example, in the PNM image format. And then on the client side, you want to convert that to PNG. So one reason why you want to do something like that is that you want to offload computation and not do it on the server side, but rather the user does it on his or her machine. Or in this video codec example that I gave earlier, maybe you deliver some file in a format that your browser natively doesn't understand, and then you also deliver a WebAssembly binary that can decode that format. And then this would be a way to use a WebAssembly program. And then in our example, we use PNGlib, which is a very famous and widely used image library. And we use an old version of that library that suffers from a textbook stack-based buffer overflow, similar to the one that I showed you earlier. And this just goes to show that you can integrate legacy C and C++ code into client-side web applications. And there's good reasons for doing that, because you want to not re-implement PNG lib in JavaScript or whatever, but you can just use this C implementation. But then what happens if this library has a vulnerability? And in our case, what we do is we take this user-supplied input image, we convert it to PNG, and then we base64 encode it and put it in the image tag and display it in the browser. And then we add this image tag to the document. And now what happens at runtime during the memory layout at runtime is what you see on the right. So this string is allocated on the heap. And then if an attacker supplies a malicious input file, then this will result in a stack to heap buffer overflow. So an attacker can supply, for example, a too large input file, yields a textbook stack-based buffer overflow. This overrides values on the heap, on the stack until it reaches the heap. And then finally, it can override this IMG tag with, for example, malicious JavaScript code. And this means that as soon as you add this code to your document, you now have arbitrary JavaScript execution, so basically cross-site scripting. And what this goes to show is that suddenly, in order to prevent cross-site scripting, you need to have a very deep understanding of the whole stack, right? You need to understand the C source code and know about vulnerabilities there and so on and so forth. And you also need to understand browser security and cross-site scripting and so on. And just to show you that this is actually possible in practice, I want to give you a very small demo. So what you can see here, hopefully, I hope you can see this browser window.
Yes. Yeah, we can see it.
Okay, awesome. So what I just want to show you is this little demo application. So just as I said, I will open an image file, a PNM file, and the WebAssembly code in this web application will convert that to PNG. And in this case, it's a beautiful butterfly and it works as expected. But now what happens if you are, for example, given a malicious input file and then you kind of do self-exploitation and open this image, supposedly image file, and suddenly you see we have arbitrary JavaScript execution, and in this case, it just opens an alert, and that's it. But of course, you could do far worse things. All right, so that was kind of the one demo that I wanted to show. This is browser-based WebAssembly exploitation. And I also showed you these primitives that you need for this particular exploit. But of course, there's much more things that we cover in our paper, much more primitives. And I can't go into detail for each and every one of them. But just to give you a rough idea, so we have seen stack-based buffer overflows. What you can also exploit in WebAssembly are stack overflows. So if you have recursive functions, or if you do a stack allocation of dynamic size, variable length arrays, or something like that, that can also be exploited. And also, if you do heap, if you have a vulnerable allocator, I'll explain that in a bit. If you have a vulnerable allocator and you can corrupt its metadata, that can also give you a write primitive. Now, as for overwriting data, I already showed you in the exploit that can overwrite heap data. You can also overwrite data on the top of the stack or further up the stack. And I'll explain that in a bit. You can also overwrite constant data. And then as for the malicious action, I've shown you this exploit in the browser. But just as there are different host environments, there's also different malicious actions that you can perform. So in Node.js, say if your WebAssembly program includes exec, then you can do remote code execution. Or if you execute it on a standalone WebAssembly VM with the WebAssembly systems interface, then maybe you import some file IO APIs, and potentially that can also be abused. And I'll explain that in just a bit. So this is the first exploit, the one that I showed you. Stack canaries and unmapped pages are not present in WebAssembly, which is why it works. And then the second exploit that we detail in the paper, and we actually also publish all the code, so you can even have a look at the proof of concept. It goes as follows. So say we have a memory allocator linked into the WebAssembly application. And because WebAssembly binaries are delivered over the network, you want to make sure that the binary is as small as possible. So what some people choose to use is not the fully fledged DL-malloc or PT-malloc, but instead they use a smaller memory allocator like EM-malloc, or WeAlloc is a Rust memory allocator for WebAssembly. And the problem is that those allocators do not use some mitigations like safe unlinking. And for that reason, if you have a heap overflow, you can corrupt metadata of the allocator, and that gives you an arbitrary write primitive. So some small allocators in WebAssembly binaries are susceptible to that. And then you can overwrite, for example, other stack frames, as we show in our second exploit. And then if on the stack there is a function pointer, we can also change this function pointer to point to a different function. So instead of calling some benign function, suddenly your program now calls exec. And we show exactly how that works in the paper and in the demo exploit online. And finally, the third exploit that we show is again starting with the stack-based buffer overflow, but this time we are not overwriting heap data or stack frame data, but instead we overwrite this static data that is allocated at program startup. And in native programs, this static data would be in the read-only section of your binary, and it would not be mapped as writable, so you couldn't overwrite it. But in WebAssembly, you can. And so say, even if you have a file name in your application as a constant string, as some fixed file name, in WebAssembly, you can override this file name to something else, and then suddenly your file write will not go to benign txt, but rather to some script, for example. And the crazy thing is, because file write APIs, C APIs typically take even the open mode as a string argument. You can even override the mode. So say instead of appending to a file, you can override the file. And we show how you can exploit that in our third proof of concept, which is also online. All right, so just to kind of wrap up, what I've shown you is that WebAssembly binaries can be exploited. And now, to end on a positive note, I want to kind of go into detail how you could mitigate those attacks. And I think the first point of mitigation is just use mitigations that are well known from native programs. And that's easier said than done. Somebody needs to spend the engineering effort to put that in mscripten and in LLVM and so on. But I think it is possible. And I think that's the kind of first step that we should do as quickly as possible. For example, put stack canaries, put control flow integrity, put fortify source, and put safe unlinking in compilers and in, for example, memory allocators that are targeting WebAssembly. That's the first kind of mitigations that we should deploy as quickly as possible. The second kind of mitigations that we can use are language-based. And those, of course, require much more effort because you need to change the language specification. And then you have 4 different browsers and lots of standalone VMs. And if you want them to pick up the new standard, that will take some time. But I think it's possible. And some of these language proposals that would help with mitigating attacks are already underway. So there's a proposal to have multiple memories. And so potentially you could have one memory that is constant and can only be read from. And that basically eradicates this attack vector of overwriting string literals, for example. Or another option is that you augment the language with a way to mark regions of memory with protection flags, say as not writable. And as I said, some of these proposals are already quite far in the standardization phase. Unfortunately, the last one is, I think, not even proposed yet. So long term, I would really hope to see a proposal like this. And finally, I think the last line of defense and the one that's most actionable to us regular developers is some general, quite simple security advice. And that is, a WebAssembly program is still only computation if you do not import anything. Of course, in order to do something useful, you always need to import some things. But what I argue for is that you please only import what you really need and keep WebAssembly binaries as small and as separate as possible. So maybe have one WebAssembly binary that does some video decoding and a different one that does DOM manipulation, but do not link the two together into a single binary, because suddenly if you have a vulnerability in the codec, it can use the functions from the client-side portion of the application. So keep modules separate and small and only import what you need from the host environment. And I think the single biggest message I want to get across is that just because WebAssembly is a new language and it's sometimes called a safe language, it doesn't mean your vulnerable C and C++ application magically becomes memory safe if you compile it to WebAssembly. It does not. And with that, I'd like to conclude and kind of give a short summary. So I talked a bit about WebAssembly in general, and what I wanted to get across is that I think it's a hugely successful and important language for the future. And I think it's a really cool technology, and there's really a variety of good reasons to use it. The second thing that I talked about is that we need to be more precise when we talk about security in terms of WebAssembly. There is 2 sides to the security coin, and one has been featured a lot and has been put very well in the design of the language, and that's security of the host against malicious WebAssembly programs. But what has been much less featured, and I argue this is very important to be featured in the future, is security of WebAssembly programs, vulnerable programs, from being attacked themselves. I've given you a bit of background on what that means on a technical level. So we have managed and unmanaged data, and all the unmanaged data can be overwritten by an attacker with a memory vulnerability. And I've also talked about linear memory, and that it is surprising in many ways because there's no unmet pages and everything in linear memory is always writable. And that's much worse than in native programs. And finally, kind of my message is that as of now, WebAssembly binaries are less secure than native execution, but it doesn't have to be that way. And there's a couple of good ways to improve the situation and at least get it on par, or potentially get it the situation better than for native binaries. And with that, yeah, I'm done with my talk portion, and I'm happy to take any other questions.
Hey Daniel, this is Paul again. Wow, just this is great presentation. Just been a very enlightening for me at least. Just a question for you regarding, you mentioned one of the mitigations about separating the WebAssemblies from each other. based on your research and experience, are there any other sort of situations or use cases where WebAssembly would make sense? I mean, just the attack vector, especially the buffer overflow, I mean, it just introduces a whole slew of different interesting attack vectors. But is there certain cases or certain use cases you think where it would make sense for WebAssembly, even if we can't mitigate everything? Maybe it'll be things that you just offload to the client side, but it ultimately, if it runs, it never gets fed back to the server side, so it'll be okay.
Right.
Yeah, so just want to get your thoughts on those.
So I think there's a couple of very good reasons why you want to use WebAssembly. So kind of one good thing is that the host security story is quite good. So if you have such an exploit on the client side, it still means all it can do is arbitrary JavaScript execution, which is bad, but it's still much better than what we had before with Java applets that are, or the JVM implementation or plugin in your browser that could suddenly lead to arbitrary remote code execution. So WebAssembly is much better than that. So I really want to stress on that. So I think it's we wouldn't gain anything if we threw WebAssembly away and rather switch to much more vulnerable, less sandboxed approaches. So I think that's good. And yeah, let me think about kind of other reasons why you would want to use WebAssembly. Well, I think the good thing is that it's a portable kind of universal bytecode. So in a sense, it opens up a lot of possibilities that weren't possible before. So suddenly you can run games on the client side without having to install anything. So from a delivery perspective, or not looking at binary security, I think WebAssembly is a very cool technology. And I think the same also goes for server-side execution. So what Cloudflare or Fastly are doing, that you can ship a WebAssembly binary to some cloud provider, and they execute it for you. And you can write your application in the programming language that you want, but you have this universal distribution format that everybody understands. And that, I think that's a really cool vision and application of WebAssembly.
Okay, thank you.
Anyone else have any questions for Daniel?
Wondering, looking at what I can find on the web for WebAssembly, and I see that ZDNet says that the website using WebAssembly use it for mining and gaming mostly. Does that sound right?
So the connection was a bit janky, but what I got is that looking at the WebAssembly website, you saw that it's mostly used for games and for cryptojacking. Is that kind of
Actually, that was an article from ZDNet. It just says that. And I see that the other user is Microsoft using Rust to build Questlet. Equivalent lets developers run multiple WebAssembly modules, but they like half of the websites ZDNet says are using it for mining and gaming.
I think initially that was true. So I think the reason why it was used for crypto mining in the beginning, kind of as early adopters, is because if you are a website owner, in order to adopt a new technology, obviously you have to wait for some minimum adoption by clients. And if you want to do nefarious crypto mining, then you don't mind it if it's only running on 80% of your victims. Well, that's still kind of good enough for an attacker. So I think that's the reason why in the beginning WebAssembly usage was biased towards these malicious applications. But 2 words on that. First of all, last year, I think one of these large crypto mining platforms, CoinHive, was taken offline. And I think since then, there has been other academics working on this, and they found that crypto miner usage has gone down by 99%. So in fact, I would argue it's no longer the majority use case, simply because that one platform went away. And the other reason is that many other use cases for WebAssembly are picking up as browser compatibility to this new feature is in the high 90s, as I showed you in the beginning. So one thing that we did in the study that I showed in the very beginning, where we also looked at the source languages of binaries, we also tried to manually analyze some binaries and look for what they are used. And we see quite diverse use cases. By no means it's only games or only crypto mining, but some use cases, for example, are so we found like a furniture planner, and that's a fully featured kind of client-side application where you can do 3D sketches and whatnot. Or as I said, Google Earth uses it I think Google Meets uses it for echo suppression, for example. So if you have a meeting in your browser and you want to do some echo suppression on the audio, that would be horrendously slow in JavaScript, but with WebAssembly, it's much faster. And so there's all sorts of these small computation-intensive parts of your web application that can make use of it. And then a third use that I think is still in its infancy, but it will become much more important, and that will also make the security story more important, is WebAssembly being used for fully contained client-side applications. So kind of not as a complement to JavaScript, but really as a replacement. And so, for example, we've seen some web frameworks in Go and Rust that you can compile to WebAssembly because people want to write front ends in those languages, right? Not really because they care about WebAssembly or the underlying technology, but just because they like their programming languages. And I think as soon as this picks up, it becomes much more important to worry about the vulnerability of those client-side applications.
Okay, well, I want to thank you, Daniel, for joining us from across the pond. And we're very appreciative, and you sure gave us a lot of information. It's a great talk. You know,
thanks a lot.
Feel free to join us for future meetings as a participant. We have meetings every month, and once this difficult COVID is over, maybe we'll visit you and you can take us around Germany.
That would be wonderful. So yes, Stuttgart is always open to you, and thanks a lot for having me. It was really a pleasure. And I hope I kind of could convince you that WebAssembly is a super important technology, and also to be wary of the security. And I really hope nothing of that will ever end up in your top 10 list. So let's keep our fingers crossed.
Right. And then some January or February, get on a plane and come out to the beach and join us out here.
Yes, I would love to. Thanks.
Great. Just a final word for everyone watching. OWASP Los Angeles meets every month on the 4th Wednesday at 11:45 a.m. Pacific time. Our next meeting will be a joint meeting with ISSA in December in lieu of our normal schedule, but it will be on December 30th. We'll be having separate breakout rooms. Feel free to join us. January, we'll resume our normal schedule. And sometime in 2021, we're hopeful to start once again with in-person meetings with lots of networking and sharing of ideas and solutions. But one closing note for everyone, I just feel that now's a good time of year, particularly during a really difficult 2020 when a lot of us have been dealing with difficult times, that we should still be thankful for a lot of things. I'm thankful for OWASP. I'm thankful for what OWASP has done for my career when I was a CISO, with all the tools and great things like cheat sheets and foundational work and great things that anyone involved in development or securing your development environment, OWASP is there for you. It's all free, volunteers worldwide. Hats off to them. I'm thankful to all those volunteers. I'm thankful to my OWASP LA board members, such as Cassio, who's right here. Thankful to Haral, who's on this call, for all the hard work he did as a co-chair for AppSec Cali for several years. And then lastly, hopeful that next year will be a lot better. And just want to end with that positive note, and we'll hopefully see you all in December. That's all from OWASP Los Angeles. Stay safe, everybody.